Okay, welcome back. In this video, we're going to talk about some more properties of finite sums. And these three properties actually they're not basic arithmetic properties like the last set of properties were. These are actual theorems that require some proof. Also, I got these from Newton. I got this slide from Newton, and they call these sums and powers of integers. That's a little inaccurate. These are sums of powers of integers. Okay, they're all sums, and they're all sums of some power of a set of integers. So, for example, the first one is the sum of the first n positive integers, all raised to the power 1. They're all power 1. So it's 1 plus 2 plus 3 plus 4 ... up to n. And it gives a formula. So you don't have to actually add up those numbers. You can just do a little multiplication and division. The second one is the sum of the squares of the first n positive integers. So notice this one is the sum as I goes from 1 to n of I squared. So it's 1 squared plus 2 squared plus 3 squared plus 4 squared all the way up to n squared. It gives you another formula that's easy to use. And then the last one is the sum of the cubes of the first n positive integers. It's not just the sum of consecutive integers cubed. It's the first n positive integers, each of them cubed. All right. Dr. G is a little nitpicky. So let's look at the first one for a second. The first one, it's credited to Gauss, Carl Friedrich Gauss. I'm going to call it Gauss's formula. Apparently, he was pretty clever. When he was 10 years old, he got in trouble in school. He was probably bored. And as punishment, or to keep him busy, the teacher said, just go in the corner and add up the first n positive integers. Add up the integers 1 through 100. Well, the kid had already come up with a formula for the sum of the first n positive integers, so he quickly was able to just plug in 100 to get the sum of the first 100 positive integers. It took him about 2 seconds. He plugged in to this little formula he had proven and derived. It was 100 times 100 plus 1 all over 2. He did the multiplication, divided by 2, and got 5,050. He didn't even have to go sit in the corner to do that. All right, and you'll see how he proved that formula in another video. But for now, let's see how to use these theorems in actual problems. So download the worksheet, and let's look at the first problem on the worksheet. So the first problem on the worksheet says, evaluate the sum as I goes from 5 to 107 of 4i squared minus 2i plus 1. So we're going to use a combination of the basic properties of finite sums in the other video. Those are just properties of arithmetic. And then we're going to use also the properties that are actual theorems, like Gauss's formula. All right, so the first thing we're going to need to do, if we want to use any of the formulas that we just saw, we're going to have to separate these terms into 3 separate sums. And we can also use the distributive property on those. So I'm going to rewrite the sum from 5 to 107 of 4i squared minus 2i plus 1. I'm going to rewrite it. I'm pulling out the 4 from the first sum, so it's 4 times the sum from 5 to 107 of I squared, minus 2 times the sum from 5 to 107 of I, plus the sum from 5 to 107 of 1. So I kind of combined a couple of properties, the associative property and the distributive property, to do this. Now, if I want to use any of the sums of powers of integers, I have to notice that these sums that I have here all start at 5. They don't start at 1. And I need to have sums that start at 1 if I want to use any of those formulas. But I can rewrite these using the associative properties. So, for example, the first one, I can write it as the sum from 1 to 107 of I squared minus the first 4 terms. So if you add up all 107 of the squares of the first 107 positive integers, and then just subtract off the first 4 of them, you'll get the sum from 5 to 107 of the squares of those integers. All right, so I'm going to do the same thing with the other two sums. So I'm going to subtract 2 times the sum from 1 to 107 of I minus the first 4 terms. And then I'm going to do it again here. So I'm going to add up the integer, the number 1 from 1 to 107, and then subtract off the first 4 terms. All right. So now I have them all in the correct form. I can use some formulas. So the first one is the sum. These are both starting at 1, and they are the sum. The first one is the sum of the squares of the first 107 positive integers, and then we're subtracting off the sum from the sum of the squares of the first 4 positive integers. So I'm going to use the same formula twice. The first one, n is 107, so it's n times n plus 1 times 2n plus 1 all over 6. This is the second theorem on the previous slide. The second one, n is 4, so it's going to be 4 times 4 plus 1 times 2 times 4 plus 1 all over 6. And then we're going to subtract 2 times, and now I'm going to use Gauss's formula twice. The first one, n is 107, so it's 107 times 107 plus 1 over 2. And then the second one, n is 4, so it's 4 times 4 plus 1 all over 2. And now the last one is just multiplication. So we're adding up 107 times. So 1 plus 1 plus 1, 107 times is just 107 times 1, which is 107. And then 1 plus 1 plus 1 plus 1 is just 4 times 1, which is 4. All right, so now we got rid of all our sigmas. We just have to do some multiplication, division, subtraction. But I'm going to cancel first. You know me, I like to cancel. It makes my life easier. So first of all, I can cancel part of that 4 with part of that 6 and that 6. Divided everybody by 2. And now I can cancel that 2 over there with those 2's there. All those denominators went away. Also, in the first term, I notice a 3 cancels with part of the 108, and the other 3 cancels with part of that 9. So that there's no more denominators at all. So now I can multiply 2 times 828,120 minus 11,536 plus 103. And I get 1,644,807. It's a little bit of arithmetic at the end, but it's not as bad as it would have been if we didn't have all those formulas to use. All right, let's do one more example. Okay, in this one, we're asked to just rewrite the sum without sigmas and without any i's. And we have the sum from 1 to n of I to the third minus 3i plus 5 times 6 over n. So notice the 6 over n is inside that sum. So because the 6 over n is inside the sum, that means every single term in the sum has a 6 over n in it. And since there's no I, it's the same in every term. So I'm going to be able to factor it out using the distributive property. So let's do that. Pull out the 6 over n, and we're left with the sum from 1 to n of I to the third minus 3i plus 5. Now, using just the basic associative property for finite sums, I can break this up into 3 terms. So I still have a 6 over n outside, and then I have a sum from 1 to n of I to the third minus 3 times the sum from 1 to n of I, because I use the distributive property there as well, and then the sum from 1 to n of 5. Now, the first term, the first sum, is the sum of the cubes of the first n positive integers. So I'm going to use the third formula of that theorem that we had. The middle term, the sum from 1 to n of I, that's just Gauss's formula. I'm going to use the first formula on that theorem. And then the last one, the sum from 1 to n of 5, well, that's just multiplication. That's just going to be 5 plus 5 plus 5 plus 5 n times. So that's 5n. So let's do it. So the first one gets the formula n squared plus n plus 1 squared over 4. The middle one gets 3 times Gauss's formula, n times n plus 1 over 2. And then the last one is just 5n. And now we can distribute the 6 over n, do some cancellation, and we get 3n times n plus 1 squared over 2 minus 9 times n plus 1 plus 30. Getting everything over a least common denominator, I squared out the n plus 1 and get combined like terms. And in the end, I simplified and got 3n to the third plus 6n squared minus 15n plus minus 42 over 2. All right. So the next video you will probably see will be a definition of definite integral. But you should practice using the formulas in the theorem, and you'll be given that theorem on the final exam, but you need to practice using the formulas in the theorem. The properties, the basic properties of finite sums, you will not be given on the final, and you'll need to practice remembering them and recognizing them and using them. All right, so I'll see you in the next video.